I'm very happy to see you guys here, and I'm very excited to visit Tokyo this time. So in this session, I'm going to talk about kernel security on Android, and currently exploiting a kernel vulnerability is the most possible way to gain root privilege on Android, and use suffer free is a major type of vulnerability in Linux kernel. So basically, a conventional exploitable use after free bug generically has a downlink pointer to the free object, and attacker also need plenty of time to refill the object and control a function pointer. I believe you can find many write-ups talking about this kind of exploitation, but according to my experience, actually, I have already trying to hunt bugs on Android for 4 years. Most use after free bug are not so that idealized. So when I got a new use after free bug, I have to analyze these bugs case by case and come up with new approach to overcome the specific difficulties in every case. So today I'm going to introduce the exploitation of 2 use after free bug I found last year, and I call them unconventional use after free. Because you cannot exploit them in a normal way. But before we start, I'd like to introduce myself briefly. My name is Dishen, also known as Ratmi, and I'm a senior security researcher of KinLab Tencent, and now I'm based in Shanghai. And I always aim to work out a universal routing exploit for Android, and till now, I've already got some trophies on Android, so you can see there is a trophy list there, and there are some CV numbers and publications. So if you have interest in my previous publications, you can check it on my GitHub. And here is our team. Actually, a picture of our team. Actually, last week we successfully become the master of Pong in the mobile Pong tournament just in Tokyo, and it's our 3rd time to become the master of Pong. And so normally our team will do some research on the mobile devices and also the laptop like browsers or Windows kernel, Linux kernel, Mac OS, and iOS jailbreak, and Android routing. That's what I do. And also we analyze the VMware vulnerability and also the IoT stuff like Tesla hacking or many other car hackings. Yeah. So we indeed do lots of research on many things. So here is today's agenda. So firstly, I will introduce the basic of Android routing and a common approach to exploiting use suffer free in the kernel. After that, let's dive into the perf subsystem of Linux and analyze the 2 unconventional use suffer free vulnerability I found last year. So let's talk about the current situation of routing Android. So while Google keeps improving the kernel security on Android these years, the situation of routing Android changes a lot. Currently, Google fixes bugs every month, and most OEM can provide an OTM update on time. So if you want to root your latest devices, you have to find 0-day vulnerabilities. And furthermore, if you want to root millions of devices at once, no matter what kind of SoC these devices are shipped with, and you must have a universal 0-day vulnerability. It means you have to find bugs in the Linux syscore or universal drivers like Bender, AOM, HMAM. But unfortunately, bugs in this available attack surface is very rare right now. And another thing we need to deal with is SE Linux. So SE Linux is a security module in the Linux kernel. It's able to provide a mechanism for supporting access control security policies. So it's just like a sandbox to userland. So currently, the policy on Android is very strict. And basically, you cannot access most of device-specific drivers from user mode. And for example, a camera driver or a fingerprint sensor driver are inaccessible. And also, many syscalls are not reachable. Last year, I found several bugs in the perf subsystem on Linux, And Google finally introduced a new feature called perf event paranoid, so that we cannot invoke a syscall perf event open from unprivileged process. And attacker also cannot send out control commands to the network device. In other words, you cannot access the wireless driver on Android anymore. So in summarize, because of the SE Linux and some other security features, the attack surface on Android kernel is smaller and smaller. And one more thing just for your information. Google introduced verified boot through the DM Verity kernel feature. So even you exploit a kernel vulnerability on Android and gain root privilege, it's non-persistent. Because every time when system boot up, it will check the integrity of the file system in every 4 KB blocks. So you cannot modify the file system, otherwise the device will enter a boot loop. But if you don't modify the system partition, you will lose root privilege after the system reboots. But I think it's not a very big problem because as a hacker, you can execute your exploit every time after system startup, so it's not a very big problem. But the next one, actually, we have some future challenges. It's really hard to bypass them. But yeah, so there are future challenges. So there will be a PAN, actually its full name is Privilege Access Never. It's a hardware feature on ARM CPU, and it will be introduced in ARM version 8.1. It's equal to the SMAP for Intel CPU, and the second one is KASLR. It's already launched on latest devices powered by the Snapdragon 835 mobile platform. And the last one is pointer authentication. It's a new hardware feature introduced in ARM version 8.3. Its purpose is to detect pointers created by an external entity. It attaches a signature to the pointer value, and this signature can be verified before a pointer is used. So I'm sure it may have some influence on the kernel exploitation, but we will see that. The only thing can be confirmed is exploiting a kernel vulnerability on Android is becoming much harder and harder. So here is an overview of exploiting use after free in the kernel. And use after free bug is easy to exploit it if it meets following requirements. The first one is the freed object has a function pointer. And the second one is attacker has plenty of time to refill the freed object. So here is an explanation. And I will show you the most conventional approach to this kind of exploitation. As I said, this approach has been discussed for a while, and you can find many tutorials online. So here we assume that there is a use after free bug in the socket, just like ping pong root, if you have ever know that. So the socket in green box is free right now. So it has a member OPS ops. It's a function table, and so normally it will point to a kernel function which is inet L control, but it's free right now. So we have a chance to refill this object by heap spray. Hopefully we can refill the malformed data to the orange box. So now the function pointer is pointing to the JOP guidance in the Linux kernel. So after that, we find our final operation is called the function L control from the userland into kernel. It will continue to call the kernel sock L control, and finally it will jump to the JOP guidance we need. So in this way, we can achieve the arbitrary kernel code execution. So till now, we can execute arbitrary code in kernel, but we still need to do something to gain the root privilege. So in the kernel, every thread has a variable which is address limit. It represents the highest kernel address you can access from the userland. If the value is -1, it means you can read and write anywhere. So after that, you can overwrite the user ID and the security ID in the process's credential to gain the root privilege. And after that, you still need to overwrite another global variable, which is SE Linux enforcing, to disable the SE Linux. So in this way, you can gain a true root privilege and do everything you want. So till now, we have already reviewed the normal way to exploit a use-suffer-free kernel and in the kernel. So in real life, the most use-suffer-free bugs I found are not perfect. So in fact, that we have more unconventional situation to deal with. And for example, if the deallocated object doesn't have a function pointer, how can you control the code flow? And that is a big problem. And also, sometimes a kernel may dereference the pointer to the object soon after the object is freed. And in that case, kernel will crash and you don't have plenty of time to refill the object. So in next part, I will explain the two vulnerabilities I found as case studies. And particularly, I'm going to show you my solution of these unconventional problems. So actually, in last year, the perf subsystem was an awesome attack surface on Android because the first thing is the perf system is pretty buggy. We've already found lots of bugs crash in this subsystem. So, and Google also know that. The second thing is it was reachable by application last year. It means any untrusted application can call the syscall perf event open to reach this attack surface and maybe crash the kernel or gain root privilege. So the third thing is that it's already been restricted by Google by a feature called perf event paranoid. I have already mentioned that previously. And so it means on the latest devices, the syscall sysperf event open cannot be reached from untrusted application anymore. But so I'm not surprised that Google introduced this mitigation on Android at the end of last year. But please note that my exploits were finished in the summer of last year, and so at that time, the perf subsystem still could be attacked. Okay, so the first bug I found is CB17 0403, and it's our defect affected all Android devices shipped with 3.10 or earlier Linux kernel. You should know that by the end of last year, most Android devices were shipped with Linux kernel 3.10 or 3.18. And so this vulnerability is really critical. And we have already provided a free software whose name is KingRoot for people who want to root their own devices. So last year, more than 14 million people successfully used this exploit to root their smartphone. And the second one is the series 2016 6787. It's supposed to affect all Android devices, but unfortunately, it requires the kernel enable a hardware feature, which is hardware perf event support in the device tray configuration before compiling. So only Qualcomm-based devices enable this option on Android. So finally, this exploit was working on Qualcomm-based device only. This is also a part of my exploit chain to bypass the Samsung Knox on Galaxy S7. And so you can check the details of my slides for Black Hat USA 27. Okay, let's have a look at the implementation of the syscall sysperf event open. So first of all, this syscall will help user to register a performance event in the kernel, and it will return a file descriptor of this event. So one of its parameters is perf event attribute. It's a description of what kind of performance event you need. And another parameter is group FD. It's optional, but it's very important. So you can use this parameter to specify a group leader of the new perf event. And multiple perf events can form a group, and every group has a leader event. So the perf subsystem maintains 3 kinds of key objects. The first one is perf event. There are 2 kinds of perf events. The first one is a software event. Another one is hardware event. And the second object is perf event context. It's a container of all perf events created in one process. And each process has 2 contents, one for software events and another one for the hardware events. And the third object is perf group and group leader. As I have already said, the multiple events can form a group, and each group has must have a group leader. So, and each perf event context has a double linked list for all group leader and another list for all events in this context. So in the group leader also has a sibling list linking all other events in this group. Actually, both 2 vulnerabilities I'm gonna explain later on has a relation to these list operations. In this syscall, it's not allowed to create a hardware event and specify it belongs to a pure software group. So it will trigger a move group operation. The syscall will move this group from the software context to a hardware context. And in this move group operation, there is a vulnerability which is CB17, 67, 87. This operation will firstly remove the group leader from the original software context and install it to the hardware context. And after that, it will remove every event from the software context and install it to a new hardware context. And finally, the move group leads to reducing the context's ref count by 1. So this is because the ref count increase 1 when you add a new group into the perf event context. So it's time to -1. But the problem is actually the move group ignores the concurrency issues. And so the use free happens due to the race condition. And the attacker can trigger the move group on the same group leader simultaneously. And the ref count to the group leader, the ref count of the context in group leader may be reduced to 0. So in this picture, you can see that there is a function called k-free RCU. So actually, if the ref count is 0, it will deallocate it. The object will be deallocated by the k-free RCU. And this picture shows you how the POC works. So, and also show you the life cycle of the perf event context in this use free. So firstly, the main thread create a software perf group. The ref count increased by 1. So after that, 2 subthreads will insert 2 hardware events into this group simultaneously. So the ref count increased by 2. And so finally, there will be a kernel function, k-free RCU will deallocate the perf event context. And that's why the use free happens. So after we successfully trigger the use free, here is the first problem we meet today because the kernel crashed soon after free the perf event context. And you can see the crash log on the right. And by analyzing the stack frame, we know that the crash happened at function perf event context schedule in. That is because the thread scheduler need to dereference this object pointer consecutively, and normally a thread can be switched in and out by scheduler frequently. So obviously, we don't have plenty of time to refill the object. So here is my solution. So to avoid the kernel crash, the attacker's thread shouldn't resume execution until we finish the heap spray. So in that case, I need to find a way to freeze the thread. And this picture explains the life cycle of the thread in modern operation system. So when a thread is created, its data is ready, and then it will start to execute. And during its execution, if the thread uses up its time slice or pre-mated by other threads, it will return back the wait list and get ready for next time to execute. But if the thread exits or is terminated by others, it will turn to a zombie. And also, there is another possibility. The thread also can turn to an interruptible or uninterruptible status forwardly. So that's exactly what I want. So if a thread turns to the uninterruptible status, it will not execute it again. In other words, the thread is frozen. So to freeze a thread, we need the thread switch to the interruptible status forwardly. So I guess the first syscall you come up with may be the function sleep, and so do I. But actually, it's not working because the syscall sys_nano_sleep will not keep the interruptible status forever. The syscall is implemented by a timer, and it will be waked up regularly in the kernel. So it cannot meet my requirements. So I found another function which is very helpful. That is the function fewtax_wait_qme. It will firstly switch itself to the interruptible status, and then it will call the freezable schedule to give up the execution forwardly. This function is very effective. So thread will not resume the execution as long as other threads don't wake it up. So now we know how to freeze a thread, and here is a picture to explain my full exploitation. And there are 4 phases. In phase number 1, it's very similar to my POC I have shown you previously. And main thread just create software perf group, and 2 subthread will insert 2 hardware events into this group simultaneously. And a function kfree RCU will free the object and trigger the use of a free. And soon after that, that is a difference. 2 subthreads need to call the fewtax_wait_qme to freeze themselves, and so that the kernel will not crash. That's very important for our full exploitation. And in phase number 2, I will try to spray the heap by using the return to dir trick to fill a malformed data to the freed object perf event context in array 1024 bytes. And the trick return to dir is very effective approach to heap spraying in Linux. You can check the paper of Black Hat Europe 2014 for more details. In phase number 3, I use fewtax_wake to wake up main thread, so the main thread will get ready to execute again. Once the main thread gets scheduled, the thread scheduler will dereference the pointer to the deallocated perf event context. So here comes the phase number 4. The deallocated perf event context is refilled by a malformed data. So the function schedule will call another function finish task switch, and finally it will call the perf event context schedule in, and it will dereference the function pointer PMU disable in PMU in perf event context. We can finally control the code flow in this way. So to summarize, in this case, actually, this bug is really easy to win the race and trigger the use of free, and it's also easy to control the code flow because we have a function pointer in the corrupted objects. So the big problem is it's hard to refill the objects because we don't have plenty of time and kernel always crash instantly. So I just propose an approach to freezing the thread by using a kernel function which is fulltext wait qme. And in this way, we can gain more time to refill the object and finish our exploitation and make our exploits 100% reliable. Okay, before we start to analyze the second bug, I'd like to explain the implementation of the perf subsystem again because it's good for us understanding next vulnerability. So actually, we just need to remember two things. The first one is the group leader has a sibling list. The second one is the sibling list is the list of perf events which belongs to this group. So actually, the next bug is also happened at the list operations. So here comes the CB17 0403. I'd like to show you the POC firstly. So there are 4 steps. The first one, I need to create a perf event. Its name is A. And after that, I will create another perf event as B and specify A as its group leader. So in the third step, I will free the object A, and it's the group leader. And in the last step, I will free the perf event B. It's the spilling of the group. And actually, the use after free just happened in the last step. And the object A may be overwritten after it's deallocated. So here is the root cause of this vulnerability. And the scenario is I created 2 perf events, A and B. A is a group leader, B is a group member. I will free A firstly, and kernel will call the function perf group detach to deconstruct this object, but the code didn't empty the sibling list of the group leader, which leads to leaving a Downing pointer in the siblings group entry. So when this function returned, the perf event A is totally deallocated, but the Downing pointer left. So later on, when I free the perf event B, the kernel will call the perf group detach again. But this time, the problem is this function will call a kernel function which is list delete init to remove the perf event B from its group and dereference the pointer group entry. But actually, it's a Downing pointer to the deallocated group leader A, so A is overwritten after free. So the picture on right is a slab poison information from the kernel message. If you want to see this log on your own device, you should reconfigure the source code and enable the slab debug configuration and compile the kernel. After that, you still need to flash the updated binary of kernel into your device. And so when the slab debug is enabled, slab allocator will refill the deallocated object with poison byte 6b. So you can see minus 6b in the picture, and it means the object is deallocated, but the contents in the red box is not 6b. You can see that there are 16 bytes are refilled by 2 kernel address. Actually, that means it's overwritten after free. So that is really an unconventional scenario in the use of free exploitation. And the only thing I can do is overwriting the free objects as following. And you can see that you can write a value to the address of the free object plus 20. And the value is also the address of the free object plus 20. That makes sense because the bug is list entry is a list entry deinitialization, and the list entry is a downing pointer. So obviously, the conventional approach to exploiting a use overfree cannot work this time because we don't have a function pointer in the corrupted object, and yeah, we only can overwrite 16 bytes, and actually these 6 bytes cannot be any value. It can only be the address of the object plus 20. So I'd like to propose a new way to exploit the vulnerability by compromising pipe subsystem in Linux. But before that, let's have a look at some useful features of the pipe in Linux. So the first thing that you can call read vector and write vector to read and write the pipe in Linux, and it can be used to read and write multiple buffers through the pipe. And the second thing is that in read vector and write vector, there is a parameter which is an array of structure IO vector with its member IO vector base and IO vector length to describe the user buffers. And also, when no contents available from the right end, the read IO vector syscall may be blocked in the kernel. And so in this way, you can use the read vector to spray the kernel heap, and the contents will stay in kernel persistently. Yeah, it's a good way to heap spraying. So this is my approach to compromising the pipe system with this vulnerability. So the first one, we just simply call the read vector, and in this syscall, it will call another function which is rw copy check u vector to confirm that every IO vector base must point to the user line space. And so after that, an array of structure IO vector is in the heap right now. And if nothing comes from the right end of pipe, the read vector will be blocked in the kernel, and you successfully spray the heap in this way. So if you can overwrite the IO vector by triggering this use overfree bug, the IO vector base may be overwritten with a kernel address. In this case, it will be the address of deallocated perf event A plus 20. So you can see the kernel address in the red box is overwritten. So actually now the user buffer is not points to the user land. It's modified and points to a kernel address. In this way, you got a chance to write a kernel address. So specifically now, if you continue to write something to another end of pipe, the read IO vector got something to read. So it's time to call the pipe IO vector copy to user. And this function will not check the IO vector base again because it's already been checked previously. So it's just assume that you are using a user buffer's address, and so he just simply use a function copy to user in atomic to copy the buffer to the address you just specified. But actually, it's a kernel address. So in this way, we can convert use after free to the out of bound write. So this picture will explain how to convert this use overfree to arbitrary read and write. And each small box represents 8 bytes in the kernel heap, and there are 5 phases. In each line, there are 2 continuous deallocated objects. The address of the first object is A. So in phase number 1, the 2 object has been deallocated. So I color the box in gray. And in phase number 2, I spray the objects with structure IO vector, and I color the box in blue. In phase number 3, I trigger the use overfree and wrote 16 bytes data to the address A plus 20. So the base address and length of IO vector was overwritten as A plus 20. I colored the overwritten box in orange. And in phase number 4, now we need to write malform data to another end of pipe to override the subsequent L vectors. And the orange box was overwritten, which means every subsequent L vector was modified, and the buffer address now is a kernel address, and the length of the L vector is 8. So in phase number 5, we can write the malform data to another end of another pair of pipe, and the buffer will be copied to any kernel address you want. So we finally achieved arbitrary kernel memory overwriting. So here is a summary. In this case, when the object is freed, the attacker has lost a file descriptor of this object. So besides triggering the use of free, I cannot do anything to manipulate the objects. And also, there isn't a function pointer to refill the deallocated objects. So what we really can do is just overwrite the address of object to itself twice, and 16 bytes in total. So I proposed a new approach to compromise the pipe system with this use of free and override the kernel memory. So here is a conclusion of the two use of free exploitation. And so most use of free bugs looks not exploitable, but there may be another way. So you need to think about it deeply and try to take advantage of some other features provided by the Linux kernel. And the better you can understand the mechanism of the Linux kernel, the better exploit you can work out. And sometimes it indeed requires the inspiration and creativity to finish the complicated exploit. So when you don't have an idea, just put it down for a while, but never let it go, because a kernel vulnerability is rare and valuable. So you should cherish every bug you found, because currently Linux kernel is really secured, and it's not easy to find vulnerability in the Linux kernel, and not like macOS or some other operation system. So so you should cherish every bug you found. So that's all of today's exploitation, but I still like to show you 2 demo videos about our latest research on the Linux kernel. So please wait a moment. Actually, the first one is that we remotely gain root privilege via the NFC on Mate Huawei 9 Pro. And I hope the sound is working. There will be a little bit background music. Just relax and enjoy the video. So the only thing I need to do is just use an NFC tag to touch the smartphone, and it will download a V8 exploit from my server and execute a V8 exploit in the web view of a third-party application. Now we are waiting the first exploit finished. So now we got a remote shell. So you can execute the command in your computer, and actually it's executed on the smartphone. And we are ready to continue our exploit chain. I'm going to execute a kernel exploit to gain the root privilege remotely. We need to wait 40 seconds, because hopefully the system will become more stable, because we already execute one exploit And now we are ready for the next one. So, okay, I just press the enter, and it prints out, success printout. It means that the kernel exploit is finished. And I successfully install a mail from the application. You can see that it's a new application. I just installed it remotely. And you can see that SE Linux is permissive, which means I successfully write the kernel address and gain the root privilege. The full exploit chain is finished by my teammates and I, and it takes us more than 2 weeks to finish it. I hope you can enjoy the video. And actually, we use a V8 exploit and also use a kernel exploit in the latest kernel. And all patches are just applied, and it's a very latest system. Okay, and I'm gonna show you another video. Please wait a moment. Oh. Okay. Desktop code blue hacker definer. Oh, actually, it's a new universal routing exploit I just made this year, because in the presentation I show you 2 vulnerabilities that was found by myself last year, and one of them is a universal vulnerability, and I just got a new universal vulnerability this year. And universal means that you can use this vulnerability to gain root privilege on every Android mobile system. And yeah, let's just start it. I show you 3 mobile phone devices, and the video was made in the May this year. And the middle one is Google Nexus 6P. It's a standard Android smartphone made by Google. And the left one is Oppo, and the right one is Vivo. Oppo and Vivo are really very popular and sell very well in China. So I made an example on these devices. But actually, my exploit can be used on every Android devices. So the only thing I need to do is just press the button and waiting for a while. Okay, the left one is already finished. The first thing, I just open a shell and type the get enforce. You can see that the SE Linux is permissive. And I'm trying to execute the SU to get a root shell. And you can see the UID is 0. It means I got a root shell, and yeah, it's rooted. Okay, the right one is also finished, but the middle one really takes some time, but it's also finished. Okay, so finally it's finished and successfully gained the root shell. And thank you for your watching. I show you the video because I like to let you know we continue our research and we really enjoy that. And yeah, normally I focus on the Linux kernel, but I have so many teammates will help me. They can provide a V8 exploit so I can finish the first video, which is again root privilege via the NFC remotely. And the second one is made by myself, and yeah, I'm happy I can achieve the universal routing exploits. So that's all for today's presentation. If you have any questions, I'm happy to answer.